Bismillahirrahmanirrahim and Assalamu alaikum. I welcome you to the lecture number 13 of online phase 2 of electric circuit analysis 1. Today we are going to discuss and know about capacitors. Capacitors are very important circuit elements. There are a lot of circuits, electric circuits, in which capacitors are found. Capacitors are mainly used or exploited for the purpose of storing energy, and the energy is stored in the form of electric field. Basically, a capacitor consists of two parallel plates, which are separated by an insulator or a dielectric. On the one plate we have positive charge, on the other we have a negative charge, and a voltage is applied. When a voltage is applied, the movement of charge takes place, which makes the current to flow. As you know that by definition, current is the flow of charge. So the amount of total charge that is stored in this capacitor is Q, and it is represented by Q is equal to CV. C is the capacitance of the capacitor, V is the voltage, and actually we have a direct proportionality of the charge, that is Q, with the potential or the voltage applied. The amount of voltage we applied, as we increase that, the amount of stored electric charge also increases. So the unit of each of these is the unit of coulomb is farad. Capacitors can be divided into two major forms. One is the variable capacitors and the other ones are the fixed ones. The fixed capacitors are used in film capacitors, for example in metal and plastic films. However, variable capacitors are used in radio receiver, for example when we have to tune our radio from one channel to another. Over there we use the variable capacitor. The symbol of a capacitor is two parallel lines with polarity indicated of the voltage applied on the plates. So as I told you, flow of charge is current, and change, this means if flow of charge is changing, that a plate taking place, that means there is a displacement of charge, and the displacement is represented over here as dq by dt, with time the movement of charge or the change in charge take place. As defined earlier, you know that Q is equal to CV. Charge is the product of capacitance and the voltage. So if I differentiate both sides of this equation, what I get is, taking differentiation on both sides, dq by dt is d by dt of CV. C is a constant. Just I told you capacitance is a constant value, so the derivative won't apply on this, and this will come out. And dV by dt will be the equation. As I told you, dq by dt in the equation 1 is equal to I, so current voltage relationship will be I is equal to C dV dt, dV by dt. This is the current voltage relationship in a capacitor. So and if I want to find the voltage across this capacitor, then what I can do is, whenever you have to eliminate derivative, you apply integral. So what I will do is, I'll take integration on both the sides, integrating both sides. So this is integrated from minus infinity to the time defined t with respect to dt, and c, as it is a constant value, the integral won't apply on it, and this is how I get dt cancels out. And by taking this term over here, what I get is, by simple mathematics, what we guess is the voltage is 1 over C I dt plus Vt naught. If we do not have any previous voltage charge stored in the capacitor, then we can take it as 0, and this will be 1 over C integral of IT of d tau. Now if I have to find the instantaneous power delivered to capacitor, it will be, as you know, power is a product of voltage and current. The current value is C dV by dt, and V was previously in the equation. And let's say if I have to find the total energy stored in this capacitor, then an integration of the power will yield the total energy stored in the capacitor. Putting values of power from A into B, putting this value over here, what I get is infinity C V dV by dt. The constant comes out of the integral, and as we know that this has the derivative over here, so whenever in integration you have the derivative with a variable, the power increases by 1 and it is divided by the same power value. So 1 plus 1 is 2, and 1 plus 1 over 2. So this is how I get 1 over CV square from minus infinity to infinity. Let's say we say that at minus infinity there was no charge stored in the capacitor. So it is simple, 1 by 2 CV square. So whenever we have to find the energy stored in a capacitor, we can use simply this equation and evaluate the at any moment the energy stored in a capacitor. So properties of capacitors are a capacitor is open circuit to direct current because it depends upon the variation in voltage. If there is no variation in the voltage, then it won't work over there. So it is the current is zero whenever we have a direct current applied across it. Voltage of a capacitor cannot change abruptly. It slowly changes up. It takes its level in infinite steps. You cannot go to infinite current immediately. It takes time in charging. So ideal capacitors are they do not dissipate any energy and there's no leakage resistance in ideal capacitors. Now as we did some mathematics, now what we'll do is we'll apply this mathematics in different scenarios. In the first scenario, we are given example 6.1, in which we have to find the charge stored on a 3 picofarad capacitor with a voltage applied as 20 volt. First of all, we have to find the charge stored, and then we have to find the energy stored in the capacitor. So charge is Q is equal to CV, which we just read, but by just inserting it values 3 picofarad with a product of 20 volt, we get to know that the charge stored is 60 picofarad. Please remember that 1 pico is 10 raised to the power minus 12. Now the energy is W is equal to 1 by 2 CV square. By putting the value, C is also defined 3 picofarad and voltage is also defined as 20. So I just insert the values and taking the square of the voltage, which is 20 square is 400. We get to know that the voltage stored in this capacitor is 600 picojoule. Now we move on to another problem, which is a practice problem 6.1. In this we have to find what is the voltage across. We have to find the voltage across a capacitor which has a value of 4.5 microfarad. If the charge on one plate is 0.12 millicoulomb, how much energy is stored? So we have the same formula. This time I have to find the voltage across the capacitor, which will be V is equal to Q by C. Q is given to me, which is 0.12 millicoulomb, and C capacitance is given to me as 4.5. I've simply put in the value and get to know that the voltage applied is 26.67. Now moving on, we have to find the energy stored. Energy stored formula is 1 by 2 CV square. Putting in the value, C is also defined in the statement of the question. We are just found taking the square of this, I get to know that the energy stored is 1600.4 into 10 to the power minus 6 joules, or you can say say at that 1.6 millijoules. Milli is 10 to the power minus 3. Moving on to example number 6.2, the voltage we have to find the current across a capacitor, and the voltage is given which is a trigonometric function, and the capacitor value is 5 microfarad. So by formula, you know that IT is equal to C dV by dt. C is a constant value 5 microfarad. Derivative won't apply on it, and the derivative will apply on this voltage. So 10 is a constant. It will come out of the derivative cos 6000 t. So by derivative rule of a trigonometric function, the derivative of cos is minus sine with the same angle, and then we take a derivative of the angle, which is d by dt of this angle 6000 t. So this all the constants gather up on the right hand on the left hand side, and a sine 6, this minus sign also goes over here, and the derivative of d by dt of 6000 t is 6000, which you might already have studied in your calculus course. So by simply doing simple basic mathematics, I get to know that the current is minus 0.3 sine 6000 t amperes. Moving on to the with the same nature of questions, practice problem number 6.2, we have to find the current through a capacitor when the voltage is given and the capacitor is given, which is 10 microfarad. So we'll be using the same formula, C dV by dt. C is constant, so it will come out of the derivative. It is 10 microfarad, and then this 75, it is also constant, so derivative won't apply on it, and we'll take derivative of the sine 2000 t. Derivative of sine is cos, and first we'll take the derivative of this sine cos 2000 t, and then the derivative of the angle, which is 2000 t. So all these constants will gather up over here, and d by dt of 2000 t is 2000. over here. I haven't missed a single step, so that you can easily follow all the mathematics. By simply multiplying or taking a product of all of this, I get to know that this comes up to 1.5 cos 2000 t. So with this, lecture number 13 wind up. In lecture number 14, we'll be doing series and parallel combinations and some other problems related to capacitor. In case you have any problem, please do let me know in the question answer session. Thank you very much. Take care. Best of luck. Allah Hafiz.